molecule of glucose, carbon 6, hydrogen 12, oxygen 6. Well, if you look at the periodic table, remember I said the periodic table is a giant table filled with conversion factors there, okay? And we're not really doing dimensional analysis there. All we're doing is addition. We're adding all the atomic masses for all of the atoms together. So if you look at the periodic table, carbon, the atomic mass is 12.011 atomic mass unit. If you just say carbon is 12, why is 12.011 now? Well, not all carbons are carbon 12. Most of the carbon are carbon 12. You also have carbon 13, carbon 14. Remember that weighted average atomic mass, and we introduced in the beginning of chapter 2 there. And when we're talking about how do we obtain the atomic mass for the weighted average atomic mass there, you have to take into consideration what is the percentage of carbon 13, carbon 12, carbon 14 in naturally occurring carbon, and what is their relative mass? Well, for carbon 13, it's 13. Carbon 14, it's 14. Carbon 12 is 12. So you have different percentage number in terms of the percent abundance there, and you have different percentage number for each of the isotopes there. So you multiply the percentage number by 12 and 13 and 14. You add them together, you end up with this number. Okay, so carbon, well, you can use 12 for most of your calculations there, since 12.011 is so close to 12 there. But only carbon 12 is assigned exactly 12 atomic mass units. And when you look at the periodic table, however, this number represents the combination or composition of all of the isotopes in there. Okay, so carbon is 12.011, hydrogen is 1.0079. When you look at your textbook there, I think the periodic table in your textbook says that hydrogen is 1.008. Oh, it's close enough. So the numbers listed in the periodic table, depending on the different versions of the periodic table, you may have slight differences on the second and third or even fourth decimal place there. That's acceptable. Okay, so hydrogen is 1.0079, oxygen 15.9994. When you do calculations, most likely we'll just use 16 as the atomic mass for oxygen here. Okay, and again, these numbers are treated as exact numbers. So we're not using the number of decimal places or number of sig bits present in these quantities. When we're doing calculation, we're doing the conversions there. We're not using these numbers to determine the sig bit. However, when we're doing the addition and subtraction there, we still need to consider how many decimal places that we have here. These, even though when we're doing the conversion there, we treat them as exact numbers, but these are truly measured quantities there. So the question here is that how do we determine the mass of one molecule? We know each carbon is 12.011 atomic mass unit. You have 6 of them. So you multiply everything by 6 for carbon. You multiply everything by 12 for hydrogen. You multiply everything by 6 for oxygen. Okay? And then you add all the 3 numbers together. That's how you come up with the molar mass there. So 180.1572. Now, please, precise number here. 1, 2, 3, 3, almost at 3 sig bit. Well, 3 decimal places there. So round it to 180.157. So with a periodic table, if you know the formula of any compound, you will be able to figure out the mass, atomic mass unit, or the relative mass for each individual molecule, if it's a mole.